Last class we were talking about what is called a concept which we usually call it as T naught concept. We did not use this term in the last class, we will use it today. What we were talking about is taking a free energy composition diagram, something of this sort for two phases, call it as let us say alpha and liquid, two phases in a phase diagram which is something like this. This side is liquid, so this is wrong. So the phase diagram should be like this. Can you tell me why did I say this is wrong, the previous one? So you have to have liquid stable on this side, okay, pure B side, liquid should be more stable at this temperature at which we are drawing, and our temperature is something like this, let us say. So at that temperature, if I extend this temperature line to both the sides, I should see that on the pure B side liquid should be stable at that temperature. That is the meaning of this common tangent. If I draw a common tangent like this, the 2 points that you are going to get here within these two compositions, which are called the C alpha liquid, C liquid alpha. Of course, some people even call it as equilibrium, C alpha equilibrium, C liquid equilibrium. Obviously here, because when I say C alpha, it is obviously in equilibrium with liquid only, there is nothing like else, but when there are three phases, then you have to specifically say it is in equilibrium with what. For example, we are going to come to eutectics in a few minutes, and once we come to eutectics, there you have to clearly say alpha composition that you are talking, is it in equilibrium with liquid or is it in equilibrium with beta. In this particular phase diagram, because there is only liquid that is left out other than alpha, if you simply say C alpha equilibrium, if you write like this, it means it is the equilibrium composition of alpha at that temperature. And whenever we say equilibrium, it is obviously with respect to some other phase. What is the second phase? It is the liquid. So when I say C alpha equilibrium or C alpha liquid, basically I am talking of the same in this particular context, in this context of where there are only two phases. So basically they are kind of synonymous. So we can call either C alpha equilibrium or C alpha in equilibrium with liquid. Okay. So now if you take these 2 points, between these two it is alpha plus liquid that is in equilibrium, and to the left of it we have already seen that it is alpha in equilibrium, and to the right of it, it is liquid in equilibrium. That means at that temperature, if I extrapolate that tie line towards the pure A and pure B, you should see that to the left of this there should be alpha in equilibrium, and to the right of this there should be liquid in equilibrium, and between these two it should be alpha plus liquid. That is how there is a 1-to-1 correspondence between the free energy composition diagram and the phase diagram. Exactly, you should see these two compositions should match with these two compositions, and on the left side it should be alpha and on the right side it should be liquid, and that is where you will see if I draw the phase diagram like this, this would not correspond to with this. Otherwise you can always do, because this is anyway schematic, I will simply replace L with alpha, alpha with L, change the free energy curves, then also it would do good. So once you draw this free energy composition diagram first, then if you are drawing the free phase diagram, it should be this phase diagram rather than that phase diagram. Okay. So this has to be remembered. Now what we are talking about is, we were talking about this particular composition which we called it as a C naught composition, and we saw what would happen if I choose any alloy, and that C naught composition I can put it on this phase diagram somewhere here, need not be exactly at the center, depends on how the free energy curves are, but it is definitely between C alpha equilibrium composition and C liquid equilibrium composition, it has to be between these two. And if I choose any alloy to the left of it and bring it to that temperature, from its high temperature from the single phase liquid state, I melt this liquid, bring this liquid to that temperature and hold it there and think what should happen. That is where we have said that particular liquid has two possibilities. One, this liquid of that C1 composition can become alpha of C1 composition, because if I choose a composition like this C1, I call it, that C1 composition will have a free energy of this is what we have seen in the last class, and that can come to either alpha having this composition or alpha plus liquid having this composition. 1 minute, let me close this. So, this is the second possibility. What is the second possibility? It can give you alpha of C alpha equilibrium plus liquid having C liquid equilibrium composition. These are the two possibilities yesterday we have seen in the last class, and then we said if you are cooling the alloy under equilibrium conditions, that means the time available is very large, then the second possibility will hold good. The liquid having that composition will split, the composition will split into these two, that means we call it as partitioning taking place. Okay, that means the composition, the B atoms which are there inside the liquid get partitioned between alpha and liquid, and that is how you get alpha having a different composition as that of the starting composition, liquid having a different composition as the starting composition. This would come out provided you are close to equilibrium. If you are far from equilibrium, that means the time available is very very short, then in such a case you would see that you would get the liquid having C1 composition would try to become alpha of C1 composition. This is what we called it as partitionless solidification. There is no partitioning taking place during this, because the composition of the liquid, composition of the alpha is exactly the same, excepting that there is only a structural change that is taking place, and such transformations are usually called as polymorphous transformations. It is a general term, whereas as far as solidification is concerned, we call it as partitionless solidification. Now, we also saw that if I take an alloy on the right side, what would happen? That means look at again this free energy composition diagram and look at the composition to the right of the C naught. That means let us call it as C2 composition. I am just trying to recapitulate before we go ahead, because it is a slightly more difficult concept for you to understand. So, let us try to see if we take up a C2 composition, and a C2 composition if I take, I can clearly see the liquid of C2 composition has this free energy. This I would call it as G of liquid of C2 composition, am I right? And this, if it has to transform to alpha of the same composition, it is not possible, because G of alpha of C2 composition is higher than that of the liquid. So, there is no chance for the liquid to spontaneously, you may always say transformations are possible from a lower free energy state to a higher free energy state always. When do they happen? When you somehow energize the low energy system. For example, you can, one best example is how are X-rays generated. X-rays are generated when a high energy beam or a particle hits an atom and knocks off an electron from, let us say, a K shell which is close to the nucleus and goes out, and this electron from a K shell going out is going from a low energy to a high energy, because it does not want to go out unless you knock out. So, similarly all excited states that we talk about are all created from a low energy state to a high energy state by putting in energy into the system. Okay. For example, a cold work state is a high energy state, and you have put in cold work into the material. So, from a low energy state it has gone to a high energy state. So, everything, so that kind of transformations are not spontaneous transformations, remember. So, you have to put in a lot of energy. Of course, even from a metastable state to come to a stable state, you need to put in some energy, which is what we call it as an activation energy. But though you have to remember, there is a difference between there is a difference between this going to this, that means transformation in this direction, and transformation in this direction. If you see that this is a metastable state going to a stable state, because this has a higher free energy going to a lower free energy. So, this there is a driving force for it. Though there is a driving force, we say there is an activation barrier for it. That is what in the first class itself we have seen. So, but if you want to go from this state to this state, which is a low energy state to high energy state, the actual energy that it has to scale up is not only this activation energy, but also this free energy difference. So, it will have a much bigger hill that it has to cross for it to go from here. So, it has to climb this and then fall here. So, if you really want a ground state material, a phase which is in a low energy state, to take it to a high energy state, you need to provide much more energy. It is not straight away just giving this much energy is not sufficient, it will not straight away go like that. So, you will see that is why it is more difficult for systems which are in a ground state, which are at a low energy state, to be taken actually to a high energy state. Otherwise, you will see that this transformation can regularly occur. That is what we are talking about. Whenever we are talking of liquid transforming to alpha, we are talking of this going to this, because at that temperature we are talking liquid is not stable. So, it is in a metastable state, but for that also you need an activation barrier, and we are saying that in this case the activation barrier is, if I now compare something like this, this is liquid of C1 composition changing to alpha of C1 composition. Here it is liquid of C1 composition changing to alpha of C alpha equilibrium composition plus liquid of C liquid equilibrium composition. It is something like this. Here the both of them, if you look at it, this is at a high energy state than this. Can you see that here? Alpha of C1 composition has a higher energy than the two phase mixture. So, you would, but it is lower than the liquid of C1 composition. So, from here it is going to this. Why should it go to this rather than going to this? Because this is smaller, because that is smaller. Why it is smaller? Because it is a short range diffusion. Clear? So, you can see that though the driving force is larger and this is a smaller driving force, I call it as delta G1, I call this as delta G2. Delta G2 is definitely larger than delta G1. This we call it as path 1, call this as path 2. For the path 1 the driving force is smaller, for the path 2 driving force is larger, but the activation barrier for the path 1 is smaller. This is what you can call it as delta G star 1, you call this as delta G star 2. So, the activation energy is larger there because of the large diffusion that is necessary. So, as a result you would see this is happening in this particular case, where compositions are to the left of the C naught composition. If you are on the right side of the C naught composition, then this is ruled out, the first path is ruled out, only the choice that is available with the liquid is only second path, and that is what happens. And what we do is, if we choose compositions at different temperatures, if we draw this free energy composition diagrams and get these compositions which are called the C naught compositions. For example, if I draw free energy composition diagram at some other temperature like this, I can get another composition which will be again between these 2 points. If I draw at some other temperature, I will again get one more composition which is between those 2 points. Like that, if I get and join all of them, I will get a line like this. And incidentally, this line would meet with pure metal melting point here and again meet with pure metal melting point on this side. Why? Because those 2 points are where the definition of a pure metal melting point is what? What is the definition of a melting point? Free energy of both the phases, the liquid and the solid, is equal, and we are talking of C naught is nothing but where the free energy is equal, free energy of liquid and solid is equal. So obviously this particular composition or this particular temperature, we now call it as a T naught. This curve is called T naught curve. So if you choose this, I will erase this and then redraw for you to reduce the number of lines. Though in isomorphous this is not very useful concept, you will see as you go to eutectics this becomes very useful. For example, if I now take an alloy composition called C1, what is this line, the top line? Liquidus, very good. So this is called TL, T liquidus. The bottom is solidus, TS, and this is called T naught. T naught is T0, okay, the naught means 0. So why we say 0? Because there the delta G is 0, delta G for the transformation is 0, that is why we call it as a T naught curve. And this T naught curve, what is the significance of it now? The significance is this: if I take any alloy and I undercool this liquid, make it completely liquid, and then I am cooling this liquid, but if I undercool the liquid to a temperature below the T naught, let us say I bring it to this temperature, there is a difference between bringing a liquid to that temperature and undercooling the liquid to that temperature. I repeat this, there is a difference between bringing the liquid of C1 to this temperature, you call it as let us say T, or undercooling the same liquid to temperature T. What is the difference between the two? It is not cooling rate.
Undercooling is below the surface.
I am saying that I have undercooled C1 to T temperature T. I am also saying I am cooled liquid C1 to temperature T. What is the difference between cooling the liquid to C1 temperature? What is the difference between? Yes, when I say undercooled the liquid to C1 T temperature, that means until you reached T, the liquid remained as liquid, it did not transform. Otherwise, in principle, when you are cooling this alloy, the solid should start forming here under equilibrium conditions. If it is normally cooled, by the time you reach this temperature T, already some solid should have formed and some liquid is left out. So if you simply are saying that I am cooling the liquid to temperature T, it means solidification has started, but the moment you use this term undercooled, it has a special significance. That means until you reached that temperature, nothing has happened to the liquid, just only the temperature has come down, liquid remained as liquid. When does this happen? It happens only when there is a non-equilibrium solidification. Under equilibrium this will not happen, only under non-equilibrium conditions, that means I have cooled it rapidly, or there are also other conditions. Do you know what is the other condition by which you can undercool a liquid? In fact, in 1950s there is a great man by name Turnbull who did special experiments to see how he can undercool the liquid. Anybody has heard of it? Yes, anybody? No, they are called droplet emulsion technique. Have you heard of that word, droplet emulsion technique, any time? No. What he said is, most of the time the nucleation occurs by what is called heterogeneous nucleation, is not it? All of us know, most of the time. In fact, if you want homogeneous nucleation, it is very difficult. That is why people are doing what is called drop tube experiments. People are also doing what is called levitation experiments, what is called containerless solidification. Have you heard of containerless solidification? If you want to see containerless solidification, go to Professor Panikumar's lab, you can actually see it happening. So, how to do containerless solidification? Levitate a liquid droplet and allow it to solidify, so that it floats in the air and then solidifies, so that you can see possibly there is no mold effect. So, solidification has to start maybe at the surface of the liquid or within the liquid. So, what Turnbull has thought is most of the time liquids always have some inclusions inside them, and these inclusions can act as nucleating sites. These are what we call foreign bodies and things like that. So, he says if I can somehow reduce these foreign particles by making the liquid droplet smaller and smaller, the probability of finding a foreign particle reduces if you make liquid into smaller particles. So, he did some kind of an atomization of the liquid droplets. So, when the liquid comes out of an orifice, try to basically put a gas so that it forms the whole liquid into the form of a jet stream, and then different sizes of particles are formed, and he very painstakingly took each particle of the solid that has formed and then polished each particle, maybe embedded each particle into something and then polished it to look at the microstructure of this particle in the cross section. And when he looked at different sizes of particles, he saw that the smaller the size of the particle, the finer the microstructure, whether it is a eutectic lamellar spacing that he is talking about or the grain size that he is talking about. He saw that the smaller the particle, the finer, that basically means the nucleation rate of that is higher, and that he calculated back and said this is happening because you have a larger driving force. Where from the larger driving force has come? Because the liquid got cooled to a lower temperature, that means liquid got undercooled to a higher and higher undercooling. So, and people have later with the various techniques confirmed that yes, this is what has happened. And so, now people actually do this droplet emulsion very regularly whenever you want to study this what is called the nucleation experiments, okay, undercooling experiments. One of the most popular technique of undercooling experiments is this. So, one way is to cool fast. Here there is no fast cooling in the droplet emulsion, the cooling rate is normal, but you have deliberately made the particle smaller, so that the foreign particles reduce, and if there is no heterogeneous nucleation, the liquid has to keep on undercooling until a particular temperature called homogeneous nucleation temperature. You all must have gone through nucleation kinetics somewhere. So, in the nucleation kinetics we define something as Tn, okay, nucleation temperature, homogeneous nucleation temperature. How do you get that homogeneous nucleation temperature? Anybody knows? How do you calculate that? All of you in second year BTech should have heard this. If not, go back to Reed Hill today and read Reed Hill, nucleation chapter in Reed Hill. Okay. I will not go into the details because we are talking of thermodynamics. I do not want to go deeper into the kinetics. I can take one extra class on that right now, but I want to avoid. So that you read a little. So, go back and read. There is a way to calculate what is called homogeneous nucleation temperature, which people call it as delta Tn, undercooling required for the homogeneous nucleation. So, if heterogeneous, yeah, basically from Turnbull's you can come I mean, of course, everything has come from Turnbull. Turnbull is the father of undercooling. Okay. So, anything that you talk of undercooling of liquid, you have to start with Turnbull. It was Turnbull who started. So, basically you try to see what is the barrier for nucleation and how to overcome that barrier. What is the barrier for nucleation? Surface energy. So, you need to provide sufficient driving force to overcome that surface energy, and from that driving force you calculate the delta T. We will come to it possibly after this. I will tell you how to calculate that delta T. So, we will see that. So, basically you are to get that delta G. Once you calculate that delta G, from the delta G we will get delta T. Okay. So, coming back here. So, if you are at this temperature, because you are below the T naught, what does it mean by below T naught? if I draw a tie line at that temperature, my composition that I am choosing is to the left of T naught curve. Am I right? That means partitionless solidification is possible. If I take the same alloy, undercool this alloy to this temperature, I call it as T1, let us call this as T2. At that temperature, that means the undercooling of this alloy is smaller now. This is, I can call this as delta T1, this is delta T1 and this is delta T2. So, I have given a smaller undercooling, and at that temperature, now again if I draw a tie line, I see that my alloy composition now is to the right of the T naught corresponding to that. At that temperature, my C naught composition is to the left of my alloy composition. If I am on the right side of the C naught composition, I have already seen here that there is no driving force for partitionless solidification. Only if I am on the left side of the C naught composition at any given temperature, there is a driving force for the partitionless solidification. So, that means what? Effectively saying that if I can bring an alloy below the T naught curve, for any alloy composition there is a T naught point. If I take this alloy, for this alloy this is the T naught. If I can come below the T naught, if I can undercool my liquid below the T naught, then there is a possibility for partitionless solidification. If I cannot undercool my liquid below T naught for whatever may be the reason, all those droplet emulsions, wherever the droplet has undercooled below the T naught, you would see a spontaneous nucleation everywhere. Otherwise, it has to wait for the surface to nucleate and the nucleation will go inwards. In fact, the way the nucleation has happened also you will know whether it is a heterogeneous nucleation or nucleated on a particular foreign particle somewhere inside, or it has nucleated everywhere and then started growing, and that is what you would see if you are below the T naught. So, that is the significance of being below T naught or being above T naught. So, you can say that if I can bring the alloy below the T naught, then I can have partitionless solidification. If I am above the T naught, then there is no partitionless solidification, and this becomes more important when we come to eutectics. Let us just look at a eutectic phase diagram. Let us look at a eutectic phase diagram. And now, if it is a eutectic phase diagram, I will have not simple one T naught curve, I will have two T naught curves. Why? Because I will have one T naught curve between liquid and alpha, I will have another between liquid and beta. In fact, I can even talk about another between alpha and beta. We will not talk right now because it is of not that much significance, because we are talking of solidification. So, what is the first one? The first one is, let us look at this curve and this curve. What is this curve? It is liquidus, TL. What is this curve? This one, solidus, TS. So, if I draw a line there, some temperature there, and then extrapolate that to that. Now, if I want to draw a free energy composition diagram at that temperature, how will it look like? It will be similar to what I have drawn before, but with some additions. What is the addition here? We will have one more additional curve. Instead of two curves, I have to now draw three curves. And incidentally, because liquid is here, and before we even draw that, let us identify the phase fields here. If I draw that tie line there, and this tie line tells me that wherever it is intersecting the phase boundaries, it defines certain phase boundaries, certain domains for phases. For example, this one, this tells me that to the left of that I have single phase alpha, is not it? Between these two I have alpha plus liquid, this is alpha, alpha plus liquid, and between these two what do I have? I have a liquid. So, and I have here liquid plus beta, and I have here beta, am I right? This is known to all of you, fine. So, if that is the case, then when I am drawing the free energy composition diagram as schematic one, then liquid should come somewhere in the middle, am I right? Alpha should be on one side, beta should be on the other side. Now, let us draw that. So, I have a liquid curve, of course, I need not have to draw like this, I can even, because liquid extends, I have a liquid curve like this, I have an alpha curve, I have a beta curve. Of course, you may say, sir, why are you closing here? This fellow will go and somewhere hit here, and similarly this fellow also will go and hit somewhere. Okay. Fine, I have 3 free energy curves. I will call this as a liquid, I will call this as alpha, I will call this as beta. Now, you will have not just one single common tangent, you will have 2, and in fact one can also talk about the third one, let us not talk about it right now. This is a one common tangent, the other common tangent is this. So, you can talk about 2 compositions here and 2 compositions here. What is this composition? Yes, this is C alpha L, perfect. What is this composition? C L alpha, composition of liquid in equilibrium with alpha. What is this? Cl beta, and this is C beta L, perfect, you are all getting it right. So, now once I know this, again I have 2 T naughts, 2 C naughts here. This is C naught for alpha liquid, this is C naught for beta liquid, am I right? I will have 1 for the alpha and liquid, I will have 1 for the beta and the liquid. So, that means on this temperature line I can put 2 points here, 1 point between the alpha and liquid, 1 point between the beta and the liquid. And this liquidus, mind you, there are 2 liquidus here, carefully see, this is one liquidus, this is also a liquidus. This is what we call it as alpha liquidus, this is what we call it as beta liquidus. Similarly, this is alpha solidus, this is beta solidus, just to differentiate, because between that on this side it is liquid in equilibrium with alpha, on this side it is liquid in equilibrium with beta, just the terminologies I want you to know. Now, if I continue this at various temperatures, I can keep on drawing similar curves at different temperatures, and at each temperature I can get one C naught alpha liquid, one C naught beta liquid, and if I join all of them I get a line like this, 2 lines, one I call it as T naught alpha liquid, another is called T naught beta liquid. These two are a very important concepts when you are talking about non-equilibrium solidification. The whole microstructure development in non-equilibrium solidification just depends on this concept. So, please try to understand this. So, now if I take this, if this is a T naught, this is a calculated value based on the free energy concept, whereas this whole phase diagram other than these 2 T naught curves, you do not need free energy calculations to get that. How can you get the whole phase diagram without free energy? By thermal analysis. By doing thermal analysis one can get the phase diagram, but by doing thermal analysis you will not get the T naught curves. T naught curves alone are fully a free energy concept. So, T naught curves can be obtained only if you have a free energy equation. So, you need to have a G alpha equation, you need to have a G liquid equation and G beta equation, and from that find out at various temperatures where are the free energies equal, finding out the intersections. So, basically equate GL with the G alpha, GL with G beta at a particular temperature, and then find out where these two are equal, which composition of liquid and solid where you have this equal, and that if you can calculate you will get this. So, these are actually calculated. You may also calculate the phase diagram, I do not say no, the whole phase diagram can be calculated from free energy, but the whole phase diagram in a large number of cases can also be obtained experimentally by doing thermal analysis, but by doing thermal analysis or any other experiment you will not be able to get this. This has to be calculated from free energies. Of course, you possibly need some experimental data to get the free energy. What is the experimental data that you need? Cp and one more. For a solid solution you need one more data, omega. Omega is the delta H mixing. So, delta H mixing also comes from experiments. That means when I take A and B, whether this A and B they have an attractive interaction or repulsive interaction, how much is that interaction again can be obtained from calorimetry, okay, that is calorimetry. So, for example, for this most of the time you do not use a DSC, even a DTA would be sufficient for if you want to get a liquidus and solidus. Liquidus and solidus, even a DTA is sufficient, or a simple thermal analysis, okay, can be sufficient, depends on of course how shallow or how deep it is. So, but here the any free energy calculations what you need is Cp data and delta H data. These two data are required if you want to really calculate the free energy for anything. If you have these two data available you can always calculate. And now if I have this, now how do I understand this? So, again the same thing, if I say if I take an alloy of this composition, let us choose an alloy of that composition. This alloy, the moment I cool it below, again cool it, undercool it, if I undercool it below this temperature to some temperature like this, any temperature of that sort, then at that temperature if I look at it, this is to the left of the T naught or the C naught corresponding to that temperature. You have to be very crisp when you start defining technically. So, this composition is to the left of the C naught composition for that particular temperature. For that temperature this is the C naught. This whole curve is called T naught, because why? Because this is giving the locus of all temperatures or locus of all compositions at various temperatures where the free energies are equal. Locus of all compositions at various temperatures where the free energies are equal, that is what is the meaning of T naught curve. So, now because we are on the left side, then I can say partitionless solidification can occur. What does that mean? That means liquid having this composition, whatever composition it is C1, would simply become alpha of C1, whereas this particular alloy under normal condition, what is it supposed to happen when I am starting cooling this alloy? The moment you reach this temperature it should start forming alpha having this composition, you all remember. So, the moment I reach here you have to draw a tie line there where it hits, that will tell you the alpha composition that is going to come out of the liquid, and then as you slowly come to lower and lower temperatures, by the time you reach the eutectic you will have more and more alpha, and at the eutectic whatever is the liquid that is left out will undergo a eutectic reaction, and in this alloy once I reach the room temperature you will have primary alpha plus a eutectic mixture. This is the typical microstructure for that particular alloy, which we usually call it as a hypoeutectic alloy, am I right? Whereas now this same alloy when I cool it rapidly to an undercooling of that sort, I do not have any eutectic, nothing. I will have simply a single phase alpha at room temperature with the same composition as that of the liquid. What does that mean? That means I have the moment I reach this temperature, at this temperature I have, instead of a two phase mixture alpha plus beta, I have a single phase alloy of simple alpha. And what does that mean? That means that I have now got a super saturated solid solution. Actually, in principle at room temperature alpha can contain only this much of B. This is what defines the solubility limit. This is the beta B amount that can be there in alpha, but now I have an alpha which has this much of B. So, single phase alpha. That is why T naught concept becomes very important, that you can completely change the way solidification occurs. If you can really undercool an alloy below the T naught, you can have the solidification taking place in such a way that instead of a normal regular eutectic solidification, primary phase and eutectic mixture, you would simply have what is called a single phase partitionless solidified alpha. And on this side, if you have, for example, if I take this alloy, now undercool it to this temperature or this temperature, whatever it is, okay, even if you undercool to this temperature, let us say, now I am here, I have to consider the other way. Here I am on the right side of the T naught, C naught. So, that means where I am on this side, and I am on the right side. What is the meaning of right side? Now you see the liquid has a higher free energy than the beta. When I am talking of alpha and beta, the right and left get inversed, is not it? So, on this side you would see liquid has a higher free energy than beta. So, partitionless solidification is possible if you are on the right side of the C naught. If I am on the left side of the C naught, beta has a higher free energy than liquid. So, partitionless solidification is not possible. So, that means again whether you are right or left, one thing is true, if I am below the T naught, if I undercool my liquid below the T naught, that is why we always this can be confusing, but this cannot be confusing. So, if I can undercool my liquid, what is the undercooling that I need to give? I should give a minimum undercooling of TL minus T naught. This is the undercooling that I need to provide. For a given alloy composition, if I can calculate what is the T naught and if I know what is the TL for that particular alloy, now the difference between this, that means this minus this, will give me what is the minimum undercooling that I should provide. If you give only exactly that, it is not sufficient, because you need some driving force, because if you are exactly there at the T naught, free energies are equal. Free energies are equal does not mean that reaction will happen. You have to be slightly below the T naught, so that the liquid has a higher free energy than the alpha of the same composition, then you would see that this. So, this is the minimum delta T naught that you should give. That is where we see that if you go deeper, this is also not sufficient. What is the problem? The problem is this. Is this clear now? So, this is what is the whole T naught concept, and this T naught concept can give you how to get extended solid solutions. These are what are called extended solid solutions. One of the basic advantages of rapid solidification processing, which Paul Dewey I mentioned to you in 1959 has discovered, is this. For example, what he has done, he has simply taken a copper silver phase diagram, okay, copper silver, and he took a eutectic alloy and cooled it rapidly. When he cooled it rapidly, he found that this eutectic alloy will give only a single phase structure rather than a two phase structure. It is supposed to give a two phase alpha plus beta, whereas he got a single phase structure. That is because he has undercooled, and to an extent that if I draw this, whatever way it is, if you have undercooled, there are other further questions that may come into your mind. We will address those things also. Sir, what would happen if I undercool below this or below this? So, those questions also we will try to answer as we go along. So, if I undercool below this or below this, I would get either single phase alpha or single phase beta. So, I can in principle get a single phase structure just by undercooling it. What I should do is, if this is the liquidus temperature and if this is the T naught, what I need to provide is this much of undercooling. That means, my cooling rate should be such that it gives that much undercooling. If I get that much undercooling, then in principle I can get a partitionless solidification. A eutectic alloy gets converted to almost like a isomorphous alloy. So, this is what we call it as metastable phase diagrams. So, eutectic vanishes completely when you do a rapid solidification, but there is a small other additional problem. What is the additional problem? The additional problem is this: the moment you take a liquid in which a partitionless solidified alpha has nucleated, what happens then? The moment alpha gets nucleated, there is a heat release. Am I right? What do we call this? Latent heat release. We call this with a particular term. What is this called? This latent heat release is called something. No. Heat of fusion, it is the same. The process, this process of latent heat release is called something. It is called recalescence. Heard of it? Yes. No? Yes, I heard both. It is called recalescence. This is nothing but the heat release when a liquid becomes a solid. Why? Because the solid is not able to contain all the heat which is there inside the liquid. So, the moment this particular area, this particular volume gets converted into liquid into solid, then immediately that particular volume releases some heat, because the earlier this volume had all liquid and it had a high enthalpy. Now, it has got converted to a solid which can contain only a low enthalpy. So, the balance enthalpy is released. Where is it released? It is released into the liquid which is surrounding it, is not it? That is why the moment you see a solid forming, there is a increase in the temperature. That is what, if you remember the moment nucleation occurs, you have a recalescence. And the moment you have a recalescence, then if I say I have undercooled a liquid to this temperature, let us say, and if this recalescence will raise the temperature of the liquid above that of the T naught, then you are in soup, you are in liquid, not in soup. Soup, liquid is also a soup. Okay. So, you are into the liquid back again. So, you cannot, that means you are in at a temperature somewhere like this, let us say, where partitionless solidification cannot occur. So, the remaining liquid cannot continue to do partitionless solidification. So, you are in trouble. So, that is why people now call that the minimum undercooling that you need to give is not just this plus something. How do I get that plus something? That plus something can be obtained simply if I know what is the amount of enthalpy that is released. Okay. So, if I know that delta H F is nothing but delta Cp into delta T, if I can put this, am I right? In principle I can put that. So, H is Cp dt. So, similarly delta Hf, where which is nothing but the difference between H of liquid and H of solid, can be taken as difference between Cp of liquid and Cp of solid and into delta T. So, if this much heat is released and if this is the delta Cp difference between the two, liquid and solid, this will be the undercooling. This will be the temperature rise, not undercooling, temperature rise because of the heat of fusion. So, if I know this value, I can calculate delta T recalescence, I call it as delta T recalescence, as nothing but delta Hf minus delta Cp, not minus, divided by delta Cp. So, if I know the delta Cp, That is where the whole problem comes. After the moment we complete this, we are going to another concept possibly tomorrow, where you will see what is the problem with this delta Cp. There is a major problem, the whole another new field of whole thermodynamics has evolved just because of this delta Cp problem. Tomorrow I will address that. So, you see that this delta R delta T R can be calculated. So, the actual delta T that you need to have is delta T naught plus delta T R. This is what is called hypercooling concept. Okay. This concept is called hypercooling. So, this is the, if you can give this much of undercooling, then there is no problem at all, because it takes care of even the recalescence also. So, you are not simply cooling up to just up to this, but to a temperature here, so that the recalescence, even after recalescence, the temperature does not cross that. So, you basically heat it to such a, I mean undercool it to such a temperature that even after recalescence the temperature does not cross the T naught, and that is what we call hypercooling concept. We will talk more about it as we go along. Okay? Thank you.